Hello, welcome to the track of the academic works of SET Experience 2020. Allan Chaubet of the Digital TV Laboratory at Mackenzie Presbyterian University will present the work Practical Tests with MMT and the Route Dash on the Transport Layer of Atsc 3.0.
Hello, my name is Allan Seiti. I'm a PhD student of Mackenzie University, and I'm going to present the paper Practical Tests with MMT and Route Dash on the Transport Layer of Atsc 3.0, which I wrote with Jorge Oliveira, Gustavo Valeira, and Cristiano Camini. And we are all from the Digital TV Laboratory of the Mackenzie Presbyterian University. Before I start, I would like to acknowledge that this work was supported in part by the National Council for Scientific and Technological Development, CNPq, and Grupo Globo, since I was granted with a scholarship of the DAI program, which is an academic doctorate for innovation program from CNPq. This is my agenda. I'll start with a brief introduction, then I'll talk about the Atsc 3.0, the MMT, the Route Dash, the tests and results that we had, and the conclusion. So we all know that digital TV is constantly evolving, from black and white to color systems, from analog to digital. We are always looking for better audio and video qualities, error detection and correction methods, power and spectrum efficiency, different antenna configurations. So what's next? Well, the MPEG, the Moving Pictures Expert Group, developed several standards for multimedia delivery, and it, for instance, developed the MPEG-2 TS, the transport string, which was widely deployed on broadcast systems, but has compatibility problems with IP, the Internet Protocol. So they realized that a new standard was needed and started to host workshops in 2009. That took to the development of MMT, the MPEG Multimedia Transport, and MPEG-Dash, the Dynamic Adaptive Streaming over HTTP. Starting with the MMT, the standard was published in 2014, and it inherited some characteristics from MPEG-2 TS, like multiplexing multiple streams in a single stream, interleaving data packets, and constant delay between packets. It is compatible with IP and HTML5, the Hypertext Markup Language 5, and is also compatible with broadband and hybrid systems. The MPEG-Dash was developed due to a market demand on the new standard for streaming services, because RTP, the real-time transport protocol, started to face difficulties, like incompatibility with most CDNs, content delivery networks. It was blocked by firewall and was not friendly for large-scale usage. So there was a need for a new standard compatible with HTTP, the Hypertext Transfer Protocol. And the MPEG-Dash standard was published in 2012. For broadcast compatibility, it was combined with Route, and it was adopted on YouTube and Netflix, for example. Now, the Atsc 3.0 is the Advanced Television Systems Committee 3.0, the North American standard. It was developed to attend the needs for the next TV generation, like having compatibility with UHD, ultra high definition, immersive audio, compatible with the internet and hybrid services, able to broadcast personalized content and interactivity, and it adopted the MMT and the Route Dash standards. The architecture of the Atsc 3.0 is organized in 3 layers. The physical layer has been built with the following technologies: the orthogonal frequency division multiplexing, OFDM, LDPC codes, non-uniform constellations, layer division multiplexing, MISO and MIMO configurations, and channel bounding. The management and protocols layers are the transport layer of the system, and the application and presentation layer is responsible for audio and video coding, interactivity, accessibility, captions, subtitles, and other services. For the transport layer, it was needed to be compatible with broadcast, broadband, and hybrid systems. So it had to be based on IP. And besides delivery of service and content, it also includes signaling, media synchronization, and the ALFAC, application layer forward error correction. And it adopted MMT and route dash methods, as I said before. So this is the basic protocol stack of Atsc 3.0. As we can see, the MMT delivers MPUs, which are media processing units, using the MMT protocol. The MPEG- delivers dash segments using the route protocol, and it is used for content delivery over broadband and hybrid services. The route is also used to deliver content that does not require real-time rendering, and signaling can be delivered by both MMTP and route. And the bootstrap signaling is provided by SLT, the service list table. So there are some usage rules for route MMTP. For linear services without an app-based feature, route or MMTP can be used but not simultaneously. So you can use either one or the other, and you can have one session or multiple sessions of any of the protocols. For a linear service with an app-based feature, you shall use at least one route session, and additional route MMTP sessions can be used, except for streaming media components in the same service. And only route is used for broadcast delivery over an app-based service. Also for SAG, Electronic Service Guide, for Emergency Alert Service, and for Digital Rights Management Service. The MMT defines tools to encapsulate, organize, signal, and deliver media and data content. Its architecture is composed of three functional areas: media processing unit, format, delivery, and signaling. This is the architecture of the MMT, and the MPU functional area is responsible for the logical arrangement of media, package, and the format of data units using the ISO BMFF, which is the ISO-based media file format. The delivery functional area contains the MMTP as the application layer transport protocol and the MMTP payload, which is the payload format and is agnostic to media codecs. So it supports new codecs, but by requiring signaling messages that identify them. And the signaling functional area manages the consumption of media data from the package and delivery for the MMTP and the MMTP payload. This is the structure of the package of the MMT. So the package provides information about the compression on the media content and the format of data units that encapsulates the encoded media. It is composed of at least one asset and one presentation information, PI. The asset contains one or more MPUs with the same asset ID that carries timed or non-timed media. It is associated with an ADC, asset delivery characteristics. The PI specifies how assets are related for consumption. It can be a MPD, media presentation description, or a combination of CI, composition information, and HTML5. We can notice that the same asset delivery characteristics can be associated with multiple assets, but each asset is only associated with one ADC. Now I'll talk about the route dash method. So the MPEG dash is based in a client-server model. This is the basic architecture of the MPEG dash. And it is composed by an HTTP server, which contains a MPD and the multimedia content. The MPD is delivered to a dash client, which becomes aware of the content available and its characteristics. The dash client can start streaming any chosen content, being able to change to a different configuration on the next available switching point. The system also is constantly monitoring the available bandwidth, so it can switch to a lower bitrate stream if the bandwidth is lower than the current bitrate being streamed. And the user can also switch to another bitrate or a different audio content if available. Route is the delivery method combined to dash for broadcasting. It supports all FAC, consists of two components, the source protocol and the repair protocol. The source protocol delivers objects aligned with FLUT, the file delivery over unidirectional transport. However, it was optimized for the delivery of real-time media. And the repair protocol protects one or multiple objects delivered by the source protocol. These two protocols are independent. The source protocol can be used alone, for example, and you can also use only the repair protocol. This could be used in scenarios where it is expected that all receivers are OFAC capable, like delivery exclusive for mobile reception and delivery for targeted regions. The packets are all LCT packets, layered coding transport packets. And to differentiate these protocols, you can use distinct route sessions, you can use distinct LCT channels with different TSI, transport session identifiers, values on the LCT header, different PSI bits when both protocols are carried in the same LCT channel. And so now I will start talking about the setup that we used. We have an audio and video source which delivers the content to the encoder either by SDI or IP. In our case, we used an SDI source. The encoder codes the AV stream in HEVC, high efficiency video coding, and AAC, advanced audio coding, encapsulates it in both MMTP and route protocols, and forwards it to the MUX using the WebDAV format. So this is our configuration for the encoder. We can see that we have both dash MMT with the configurations that I said. The MUX adds signaling information to the encoded content. So this is our MUX. It is split in a few areas like the packager, NRT, SAG, signaling, and finally what's called the multiplexer. And the scheduler adds transmitting data in the stream and forwards it using the STL, Studio to Transmitter Link protocol. So this is the scheduler, and we can also see some configurations that were set for broadcasting. And finally, the modulator converts the STL string in RF for a transmission chain. And here is the modulator that we have. And also we have a transport analyzer that monitors the STL string. It can also be connected to the output of the MUX, so we can either analyze the MMTP en route protocol's output straight from the MUX, or we can analyze the STL provided by the scheduler. So this is the STL in the transport analyzer. We can see some of the configurations for the physical layer, like the bandwidth, channel, and some other configurations in the preamble, the modulation order, which is a 64 kAM and NUC, and the transport analyzer monitor looks like this. Since we cannot see much, I'm going to zoom in each part. So starting with the input string info for MMTP, we have a total rate of approximately 3 megabits per second. We can also see the signal rate, the codec of audio and video, and the resolution and the frame rate. For the route session, it looks similar. However, we could note that the signal rate is larger for route in this configuration. The LLS, low-level signaling, contains the SLT and system time. The SLT describes the service. It provides identification of used protocol, major and minor channel, which are physical and virtual channel. So for the first service, we have the channel 60.1, and for the second service, we have the channel 60.2. And we also can see this SLS protocol, which the value 2 means it's an MMTP service, and the value 1 means that it's a route service. And the system time provides the UTC time zone information. The service layer signaling SLS for MMT contains the USBD and the complete MPT table. The USBD user service bundle description links the MPU components to allow video playback. The MPT table is the MMT package table and contains the information that permits the consumption of received packages. For the route dash configuration, the SLS contains the USBD as well, the STS ID, and the MPD. In the USBD, we have this base pattern information, which is a character pattern to be used by the Atsc receiver that matches with any portion of the segment URL, Uniform Resource Locator, used by the dash client. The STS ID, service-based transport session instance description, provides the overall session description information for the transport sessions. The RS route session contains the elements that provide information about the route session carried. The LS contains elements that provide information about the LCT channel. And the SRC flow contains elements that provide information about the source flow. The MPD provides general media information. So now I'm going to play this video that we recorded with both services being transmitted. The route is the one on the right, and as we can see, it is a little delayed in relation to the MMT service. So for this configuration, we could notice that route was a little delayed. For the conclusion, MMT and MPEG- were initially developed for different purposes, different architectures. Due to this reason, both are compatible with ISO BMFF and ALL-FAC. The delivery protocol was signed on SLS protocol. Dash uses MPD for content description, while MMT can also use a combination of CI and HTML5. For the setup configuration used in the tests, route presented a larger overhead. The stream from the route dash service was delayed in relation to the MMT service. Dash has been vastly deployed, so there are many more tools and equipment compatible with it. And for future work, we could test with other AV sources and for different configurations such as targeted advertising, multi-view, multiple audio streams with additional services like the emergency alert. We could also measure the latency of these systems for distinct scenarios. This is our references. And thank you, Seth, for the opportunity of presenting this paper. Thank you for watching, and if you have any questions, please feel free to email us.
Allan, thank you very much for the presentation. If you have any questions for our speaker, please contact him via email.